Okay. Good morning, good afternoon, good evening. My name is Silvina Ponce-Dawson, and I am currently the president of the International Union of Pure and Applied Physics, IUPAP, the only union which covers all areas of physics. On behalf of IUPAP, I am very pleased to welcome you all to the last 2025 colloquium of the series on Physics for Society that we started to organize this year together with UNESCO, the United Nations Educational, Scientific and Cultural Organization. In 2025, the series focused on the themes of the International Year of Quantum Science and Technology, but we expect to continue it next year, covering the themes of the International Decade of Sciences for Sustainable Development. We invite you all to stay in touch with us to learn about these forthcoming colloquia. The link will be provided on the chat. Using this link, you will also be able to access the channel where the videos of all the colloquia are posted. I mentioned that this year the series focused on themes related to quantum science and technology and started with a beautiful talk by Nobel Laureate Alain Aspect. We are now about to end this year's cycle with what we expect will be a very interesting dialogue between the Nobel laureates Phillips and Alain Aspect, who will share their quantum views with the moderation of Luis Orozco from the University of Maryland. Christine Dove will formally introduce all three of them. Before leaving the floor to her, I want to thank all those who have made this series possible, especially all the speakers and those who have worked in front or behind the scenes: Christine Dove, Amal Kasri, Jin Yang, Sandro Scandolo, Francesco Zavino, among others. Today, my deep thanks go to Phillips and Alain Aspect, who have agreed to share their quantum views in public, and especially to Luis, who was key to make this closing event possible. So please, Christine, I leave the floor to you.
Thank you very much. So a warm welcome to this fifth IUPAP UNESCO International Colloquium on Physics for Society. So as we bring 2025 to a high note, it's a pleasure to introduce this concluding session. So my name is Christine Dove, and I work at the European Spallation Source, the ESS in Lund in Sweden, and I'll also serve as chair of the IUPAP Working Group 14 on accelerator science. So as mentioned by Silvina, and as you may have seen on our IUPAP UNESCO webpage, so the recording of our 4 previous colloquia are available. So those sessions highlighted the role of the UN International Year of Quantum Science and Technology and the intersection with industry, innovation discovery tools such as the light sources, showing case for the collaboration in Africa and around the globe. So following our first colloquium this year, with Professor Anne Lhuillier on April 14, which coincide with the International Day of Quantum. So it's a great honor to conclude this year today with Professor Phillips and Professor Alain Aspect, who will share their insight in quantum views. So it's a rare opportunity also for you to ask questions and witness the exchange of ideas between two of the greatest scientific minds of our time. So now let's introduce our special guest. So Professor Phillips is a 1998 Nobel laureate in physics. So he was recognized for developing techniques to cool and trap the atom using laser light, allowing scientists to control the motion of individual atoms with extraordinary precision. So this groundbreaking work has paved the way for major advance in quantum measurement, high precision spectroscopy, and the development of atomic clock, which is now essential tools in science and technology around the world. And Professor Alain Aspect, is a 2022 laureate as well, Nobel in Physics, celebrating also the pioneer on experiment on quantum entanglement, which confirmed the violation of the Bell's inequation and provided crucial experimental support for the foundation of quantum mechanics. His groundbreaking works has not only deepened our understanding of the quantum theory, but also paved the way for modern quantum information science, quantum communication, and quantum technology. And our moderator today, so Professor Luisa Orozco, who is a professor emeritus of physics at the University of Maryland and a fellow of the Joint Quantum Institute. So his research focuses on quantum optics, precision spectroscopy, and test of fundamental symmetries, so using the phantom atom. So he's a fellow of the American Physical Society, the Optical Society, and the Institute of Physics in UK. And he's widely recognized for his contribution to quantum science and education. So on this note, so I will let Professor Orozco initiate this promising open dialogue and reflection section. And afterward, we will open the floor to your question, which you can submit in this Q&A box. And we will conclude with so Dr. Amal Kasri, who represents the UNESCO and play a key role in fostering international collaboration and outreach in science and education. Now, without further ado, so Luis, so the floor is yours.
Well, thank you very much for the introductions, and I should start by thanking very much Silvina for the invitation to try to organize this, and to Alain and Bill for having agreed to join. So let me start by asking both Alain and Bill, since you were involved very early on this, let's say, adventure of the International Year of the Quantum, or what do you think, let's start with Bill, the main impact of the International Year of Quantum and Technology has been or will be?
Well,
since you started in Paris. Okay.
Yes, I think that having an international year like this has helped to focus people's attention on the impact and significance of current research in quantum. Now, having said that, I have to say that it's always difficult to define what we mean by quantum research. The entire world is quantum. Everything that we do is affected by the fact that we live in a quantum world. Essentially, all of the modern technology that we have, the computers and the connections that allow us to be on this Zoom conference, the cell phones, mobile phones that we carry in our pockets all the time, all depend upon quantum mechanics. But today, when one speaks of quantum, it seems that we mean something beyond that. We mean technologies or scientific investigations that make particular use of some of the weirder aspects of quantum mechanics, like superposition and entanglement. And I see that Alain already is reacting and probably has something more to say about this. But I think that the International Year of Quantum Science and Technology has, on the one hand, focused attention on these kinds of investigations, but also has focused attention on what things might be possible in the future. Now, we have a saying that I'm very fond of, that prediction is difficult, especially about the future. And that is particularly true of quantum science and technology. I'm fond of saying that if you had asked people like Heisenberg and Schrödinger in 1925, 1926, what would be the results of this new science that they were just developing, they might have responded, well, we can explain the spectra of atoms. We can, perhaps if we're lucky, we may be able to get some new insights into how chemistry works. I'm confident that they would never have been able to predict the transistor, the development of semiconductor electronics, the way in which quantum mechanics has changed the lives of almost everyone on Earth. And so, in the same way, I don't think that we can predict the way these aspects of quantum mechanics that we're focusing on during this year, I don't think we can predict how they will change our lives.
Thank you, Bill. Alain, I'm sure you have opinions. Great.
Sure, but if you let Bill speak first, what is left for me then?
No.
So you should be careful.
Okay, I try.
Anyway, I can try to answer the first question. What was the impact of this year? Yes, as Bill says, it draws attention of politic people and of the public on quantum physics. And I've taken the opportunity to giving many popular lectures about quantum physics to the general public. And probably the fact that it was a year of quantum science and technology helped to attract people to these talks. And to add something about the last statements of Bill about we cannot say anything about future, what I like to tell people is the crucial dates for the development of what I call the first quantum revolution, and then I will speak of the second. Quantum mechanics emerged between 1900 and 1925, okay? In 1925, we can say they had the right equations, okay? Schrödinger equation, etc. It took another 20 years, 22 exactly, to have the first transistor, and I emphasize in my talks the fact that transistor was not invented by a guy trying at random in his garage in California or who knows where, okay? It was invented by the best physicists of the time, trying to use and succeeding in using quantum physics to describe the motion of electrons in semiconductors, okay? And then another 13 year, 1960, and then you have the laser. And once again, it has taken a lot of time. And then many transistor is integrated circuits. It still demands some time. And finally, by the end of the 20th century, the society begins to be fully impacted by computers. And so it takes at least 80 years, maybe more, between the initial research on a subject, the initial emergence of a subject, and the moment when it transforms the society, in our case, society of information and communication. Now, as Bill said, everything is quantum, but in fact, when we speak of quantum science and technology these days, we mostly think of the new technologies which are permitted by the progress that we have done in the recent decades. First, emphasizing the fact that entanglement is really definitely different from superposition. Bill is going to argue that it is superposition, but it's not superposition in our space, it's superposition in an abstract Hilbert space, and in fact, is not about a single object. So really realizing that entanglement is different was very difficult. Somebody as smart as Feynman in 1960 in lectures of physics say entanglement, nothing different from the superposition principle. But 20 years later, in 82, he say entanglement, maybe I underestimated it. And then he started to announce the idea of quantum computing, okay? So entanglement is one of the ingredients of the second quantum revolution, understanding that with entanglement, you can do new things. And the second thing, which is in my opinion, as important, is the fact that experimentalists, starting in 1970 with Hans Dehmelt, were able to catch, observe, and manipulate single quantum objects. Okay, Dehmelt did that for an electron, and then we have learned how to do it for single photon, single atoms, etc. And for me, the ensemble of realizing the power of entanglement plus the ability to manipulate single quantum objects opens the new field. This is what we have in mind when we speak of science and technology now.
Thank you very much, Bill and Alain. And I will start with Alain now, the next question. Okay, because I think you have both, you and Bill should tell us, try to go back in your life. And and I think it would be very interesting to just know, what did you think when you were first exposed to quantum mechanics? I don't know if this happened when you were in your late teens or early 20s, but can you tell us? Because I know at least Alain has some interesting stories.
Well, when I was in the last year of high school, I had a really outstanding teacher, and he was showing us the fact that when an atom goes to a level to another one, or he was telling us that when atom goes from level 2 to level 1, it emits a photon, etc. But on the other hand, there was another part of the program which was about interference and diffraction. And I must say that for me, I had a hard time understanding how you can reconcile the two visions. The fact that sometimes there is a photon emitted with a given wavelength, and on the other time you have interference and diffraction. And you know, later, so this was in 64, okay? And later, I could discuss with Claude Cohen-Tanuji, and Claude Cohen-Tanuji told me that when he was in Les Ouches in 64, he had exactly the same question. And Claude Cohen-Tanuji understood how you can match the two points of view when he heard the lecture of Glauber in Les Ouches in 64. And I understood myself when I heard Claude explaining that in a lecture in Collège de France in 74. So, you know, with 10 years of delay, I was asking myself the same question as Claude Cohen-Tanuji, and I have an answer 10 years later. So for me, it was really the most difficult part of it. But and then I had no good education in quantum physics, because this was high school, so the teacher tells her things, but you don't really understand how it works until the moment when I bought the recently published book by Cohen-Tanuji, Dieu and Lalauet. I was in Africa in 72, and I started learning the whole formalism in that book. And I must say that I found this formalism so clear that for me it was immediately clear how you can use the equations to render an account of this duality, wave and particle, etc. But I must say that I also immediately saw that if the mathematics are clear, when you try to make images in the real world, then the images are not so clear. And this is why I was so enthusiastic when I found the paper of John Bell and say, I want to work on that, because maybe at the end I will have a clear image. Now I have to admit something, I still do not have a clear image, except that, or I have to admit crazy things like non-locality, etc., etc. Okay, so, you know, I think that maybe quantum physics belongs to this, understanding quantum physics belongs to this kind of things where people say that it's only when the previous generation dies that the new generation has no more problem, okay? It may be like that. What do you think, Bill? Do you think that we will ever fully understand quantum mechanics, or it will just the younger generation who will understand it?
Well, I think that the question of fully understanding quantum mechanics, the problem with even saying something like that is that it may be impossible to understand quantum mechanics in the same way that we have understood classical mechanics or classical electromagnetism. It may be that the concept of understanding is too narrow because of the experience that we've had with 19th century physics. and trying to apply the same standards of understanding to quantum mechanics may be totally inappropriate. In the 19th century, it was considered perfectly reasonable to ask a question like, where is the particle and how fast is it going? In the 20th century, we realize that is not a legitimate question. And I think that it may very well be that people who have been brought up on classical physics will never fully understand that quantum mechanics is something different. But what do I know? Well,
Bill,
go ahead.
Can I interrupt you?
Sure.
I like to argue with Bill. We
That's
love
great.
arguing with each other. I disagree with you on the 19th century. In the 19th century, people could not understand how an electromagnetic field can propagate without any support, okay? And we, the young generation, have been brainwashed and they say, oh, electromagnetic field goes in vacuum, and we accept that. And so, you know, it may well be that the problem with quantum mechanics is about the same. When the future student have been trained from the beginning with these ideas, maybe they don't even understand why we ask this question. I'm not sure, but I'm just emphasizing the fact that even Maxwell could not accept the idea that the field was without any support, that it was in the vacuum. And now we have no problem. Well, another thing, instantaneous law of universal gravitation. This is crazy. And Descartes was trying to have vortices and stuff like that. And then we accept the idea that we have the sun was an instantaneous attraction to the earth, etc. Once again, we have been brainwashed for that, and maybe the future generation will be brainwashed about quantum physics. But personally, I don't like it for the following reason. I think that asking this crazy question and having crazy images like the ones I have, including non-locality, etc., gives me intuition of strange phenomena. And once this intuition tells me, oh, if you do that, it will be extraordinary, then I go to the math, I calculate to see if my intuition was good. So personally, I need to ask myself this question, to have answers which are crazy, inconsistent, bizarre, and this inconsistent and bizarre answer allow me to have intuition. Bill, don't tell me that you don't have images for guiding your intuition.
Well,
Let's hear Bill.
as you well know, I've often said that I consider myself to be an acolyte in the Church of Shut Up and Calculate, but that in
But you
spite
never shut up.
That's correct.
but in spite of that, that I'm perfectly willing to visit other congregations on the weekends. And so I believe with you that it's a good idea to carry images, but you shouldn't be wedded to one particular image of, or as we say, interpretation of quantum mechanics, because that might limit the kinds of imagination that you can have. I completely agree with you with what you say about Maxwell. In fact, I often imagine that one of the things I would most like to do is to ask Maxwell why, after having created what we now call Maxwell's equations, which so clearly show that you don't need an ether, why he still was wedded to the idea of an ether. It's a mystery to me, and I'd really like to know what his thinking was about that. But to go back to the question that that Louise raised about when we first encountered quantum mechanics, my first encounter with quantum mechanics was reading a book when I was a teenager in high school by George Gamow called 30 Years That
Oh,
Changed Physics. And I
Oh, you read
recommend
that
it
so
still
young?
today as a wonderful book. And it was the adventure that Gamow was able to transmit, the adventure of the new kinds of discoveries that were being made. Not so much explaining what quantum mechanics was all about, but conveying that sense of adventure. And it's one of the things that solidified my own determination that I would become a physicist. When I first started to study quantum mechanics, I really did not understand how deep it was. It was only when I was in graduate school that I slowly began to understand uh, how uh, how strange and how wonderful quantum mechanics was. I can remember when we first heard about the experiments of Clauser, that I completely misunderstood the the concept of entanglement that was being tested. Uh, that it seemed so obvious to me that if you detected a right circularly polarized photon on one side, that you had to detect a left circularly polarized one on the other. And I didn't understand anything at all about it was necessary to measure in different bases in order to see the non-classicality of the correlations. And it was only slowly listening to people like Alain that I began to appreciate just how strange quantum mechanics is. So for me, it was a very slow process. I was very ignorant of the deep beauty of quantum mechanics when I first encountered it.
If you speak of a Clauser experiment, in fact, for me, I understood. I was exposed for the first time to entanglement and to the problem of entanglement because I discovered all that in the paper of John Bell, the 1965 paper of John Bell. Because in the first part of the paper, he explains what is entanglement, what is a prediction, etc. And in the second part, he shows you how bizarre it is. And so I was immediately exposed to the weirdness of entanglement because it was so well explained in that short paper of John Bell. So I was lucky from this point of view. And then I read the paper of Einstein, Podolsky, and Rosen, and I immediately realized what is, in my opinion, the most impressive part of the paper, which is the fact that they immediately speak about entanglement at a distance. Because they say, okay, what you do here cannot influence a particle which is far away. And that's all the point. Because when you read the reply of Bohr, excuse me, but I am going to say something which is not so nice about Bohr. Bohr makes an argument saying, oh, what you measure depends on the apparatus, etc. But he speaks as if it was an apparatus on a single object. And he totally avoids considering what is the key of the ancient Podolsky-Rosen paper, is that what you do on one side seems to change the situation of the other side. And Bohr does not address this question. And you know, for me, it was really in that order. Bell paper, Einstein, Podolsky, and Rosen, and Bohr. And from the beginning, I understood that the key was there.
Okay, look, I think this has been wonderful. And the next thing I wanted to ask you, and you already showed and said it, so I'll skip it, which is the great influence that you have had since you, probably before you started to share that office in Roulemont, one on each other, which has been not only...
No. I was not in Roulemont. I was in Institut Optique. I insist. I was in
No.
Institut Optique.
When you and Bill, the first
pardon.
time you share an office, if I remember correctly, was in Roulemont. When you had already, both were in the search of cold atoms. Am I correct or not?
Yes, for cold atoms, yes. Well, first you have to know that every morning I had 1 hour of my time occupied by the various questions of Bill about French language. You know, the day before in the newspaper he was noting many questions, and so in the morning there was at least half an hour, sometimes an hour of teaching him answering his question, because he's a nitpicker, not only in physics but also in French, okay, in a foreign language.
And in commas and in English and in everything, right, Bill?
Right, and we should emphasize that the correct translation of nitpicker into French is pinailleur.
Okay, look, let's
So what do you want to know there? Did we talk about physics? Yes, of course, and not with equations, with plenty of images, waving hands, etc.
Yes.
We love talking with images. Right, Bill?
Yes, and I think that the influence of Claude Cohen-Tanucci was very strong. Claude was not satisfied with an explanation that only involved abstract mathematics. Claude always wanted to have a concrete image. I think this goes along with what Alain said about the importance of such concrete images, and I think that in laser cooling, this was illustrated very clearly. The kind of image that Claude and Jean Dalibard developed to describe what was happening with subdoppler laser cooling was really vital to allowing progress in that field, as opposed to simply writing down the equations. I remember something that Jean told me during that time. He said, if you solve the optical block equations, you will get the right answer, regardless of whether you understand anything about the problem or not.
Allow me to add something about that, and it's a lesson I try to teach to younger people. I fully agree with what Bill has said now. You can solve the optical block equation, or let's say solve the master equation for the density matrix, etc. But I think that a very important progress done in the second quantum revolution is, since we allow ourselves to consider single quantum object, we began to think in terms of what is known now as quantum Monte Carlo. The formalization of quantum Monte Carlo was something beautifully done by Carmichael, Dalibard, Molmer, and these people. But before they did this formalization, we all, for instance, somebody like me, I was already thinking in terms, I have a single pair of photons. I make a measurement on the first one. What happens on the second one? And I've been teaching all my life to my students, try to think of images with your object, and maybe at one moment you need to make a calculation with density matrix, but only at the end, only when you have thought about it and that you have the intuition that something interesting is happening. Yeah, I'm sure Bill, it's exactly what Bill had in mind when he said, if you solve the optical block equation, it's good, but it doesn't help you to understand.
Well, I'm glad you brought up the idea of the quantum Monte Carlo, because
Yeah.
the original motivation, at least as indicated in the papers that were the first papers that came out from the people you mentioned, was that you could make a more efficient calculation of a difficult problem that had many degrees of freedom. But I think that, in fact, the biggest impact of the quantum Monte Carlo method has been changing the way in which we think about a quantum problem.
We violently agree, Bill.
Very good. So let me just remind you, Peter Soller also had something to do with that in the formalization. I think
it's true. It's true.
He was doing a calculation.
Yes, absolutely.
Yeah. So anyway, so
absolutely.
Look, this brings me to a very. I thought this would be very interested for the people to hear. So when you first, each one of you, and I again will start with Alain, when you first did the work that won you the Nobel Prize, that's about 40 years ago, more or less.
More than less.
Okay, all right. So the thing that I would like to know, and I think the people would like to know, is for your personal opinion, what was the most interesting and important consequence of it, both in science and technology then, and from what you have seen after more than 40 years, what is the thing that strikes you that, as let me just use what you said before, that is the transistor for you now? Okay, Alain.
Okay, so there are several questions in your question. First,
Yes, indeed.
my reaction when I got the result was to say, okay, once again, we tried to corner quantum physics, okay, and it survives, okay, and isn't that unbelievable that it can survive any kind of subtle tests that we have for it? And probably, I'm not sure I realized it as explicitly as I said recently, but it totally influenced my way of understanding quantum physics, just as we said with Bill, by thinking of objects evolving, etc., etc. Now you must realize that I never thought in that time that there would be any application. And this is why when Claude, I thought that I had settled a debate between Bohr and Einstein, and you know, that's good for a young physicist. You settle a debate between Bohr and Einstein, you can be proud of it. And then Claude Cohen-Tanuji gave me a call and saying, I want to start working on something, laser cooling of atom. You know, there is an American guy, Bill Phillips, who has started that. So we should do it because he seems to be good. So we should do the same thing. Do you want to come with me and work on laser cooling of atoms? And then I worked 100% of my time on laser cooling of atom, forgot totally about entanglement and all this stuff until by the late 80s, maybe early 90s, I'm not sure, but in the end, a young student, Arthur Eckert, came in front of me and said, do you know, Professor Aspect, that with entangled photon we can do quantum cryptography? I say, what? Please let us sit down and explain me what that is. Until that moment, I had not realized that there could be any application of entanglement. And of course, now I'm amazed of all these quantum technologies based on entanglement, which are progressing, which have not yet changed the society, I must admit, but they have changed the way we see the technologies.
Okay. Bill.
Well, it's not so easy to answer because so many things have come out of laser cooling that it's hard to, and so many things that I didn't anticipate, that it's hard.
Bill, I know how important laser cooling, since you are an employee of the National Institute of Standards and Technology, is for a good clock. But I would like to know, in your opinion, what you just said, of the things that you didn't anticipate, what's the one that really
exactly but
excites
first,
you?
Yeah, but first let me emphasize how, in a sense, different my experience was from Alain's. Alain's is studying such fundamental ideas about entanglement with a clear idea that there's not going to be any application of this. I was working on something exactly because of the application. I started doing laser because I am at the United States National Metrology Institute. And I thought among the things that I could do, that laser cooling would help to improve metrology. Now, what I didn't anticipate was the other things that could be done. I mean, laser cooling has improved metrology. The best clocks that we have today are laser-cooled clocks. But the things I didn't anticipate, the best clocks are not just laser-cooled, they're operating in optical lattices. We, in a sense, accidentally discovered that optical lattices were working in our laboratory, even though the idea was already very clearly laid out by people like Letokov 10 years earlier. But today, the best neutral atom clocks are done in optical lattices. I never thought that would be what would happen. I never thought that laser cooling would lead to Bose-Einstein condensation. And think about how important Bose-Einstein condensation has been to the pursuit of atomic physics. I never imagined that laser cooling would result in the ability to manipulate single atoms and be used to make quantum processors. There are so many things that I couldn't imagine that have turned out to be completely new fields of research that I am, in some cases, simply an amazed spectator of these new fields of research. And so for me, it's been absolutely remarkable and satisfying that laser cooling has produced so many things, and at the same time terrifying that so many things are going on that I can't possibly follow them all.
Okay, thank you very much, Bill. So, following a little bit on looking at the future, as Alain put it, right, that the impact in society is not the next day after the scientific discovery is made. I look at, let's just go classical physics. And yes, Newton got his ideas, and it took more than 200 years or so for ideas like energy and entropy to start to make a real technological impact. Did Newton have the idea of entropy? I don't think so, but I am not an expert on all the ideas that he may have been having while doing alchemy, but that's all right. But what I would like you to explore, and I would like to ask first Alain and then Bill, is okay, so quantum physics is a little bit more than 100 years old. Certain things, just as Alain told us, such as entanglement, are now resources, right? They are very, very important. So do you foresee or dream of new concepts that will go beyond entanglement, that may even have more impactful technological things in the future that we can see? Do you smell something in the air, or you just would say, well, let it evolve and let's support fundamental science so that technology can improve?
Well, let me answer first, because my answer is I don't know. You're absolutely right that the firmness of the distinction between concepts like kinetic energy and momentum were not really appreciated, and still confuse students today. I think it's likely that as we become more comfortable with using concepts like entanglement, that quantification of how much entanglement a system has may become really important. The trouble with even saying that is that we know that when we go beyond bipartite entanglement, that we have a real difficulty even distinguishing between systems how much entanglement there is, let alone having a good measure of it. So I think we still need a breakthrough in that sort of thing. But I think Alain has a more mature understanding of
No. I was going to say exactly the same thing. It seems to me that we need an effort and a clarification about exactly what you said. What means exactly entanglement when we have several particles, etc. We need a clarification as important as the one which appeared when they invented the concept of entropy. Okay, I'm deeply convinced that this will happen sooner or later, and then it will really change the vision of people about quantum information, quantum processing, etc. But when you look at, I love history of science. When you look about thermodynamics, isn't it strange that Carnot established basically the basis of second principle of thermodynamics long before Joule established the first principle of thermodynamics. It's really ironical, and so who knows what will happen with all that. But I am deeply convinced that in the domain that we call theoretical quantum information, something will happen in the spirit of defining some kind of quantity equivalent to entropy, but for entanglement. But it is wishful thinking, okay? I have no idea of how
That's
it may
fine.
happen.
That's fine. But I think it's good. I recently was telling my students, you have to accept that we, the old guys, are very kind to you, young people, young generation. They are very nice and important, open questions still for the new generations, both in the, as you just said, well, what is it once you go past two bodies that are entangled? We don't really know. And then there is the other, I would say, that falls more in the technological size. What is useful entanglement?
Let me tell you that we reached the 40 minutes, so just for you to know.
Okay.
Thank you.
Thank you. Thank you. So we have 5 minutes to go. Yeah. So,
and then we open for the questions from the public that we already have 8.
Yeah.
Can I say something about
Bill, let's hear.
Entanglement of many particles? It seems to me that one of the wonderful things about these big efforts for building a quantum computer, I am involved in one of them with neutral atoms, with Antoine Boès and the company Pascal. I think that one of the beautiful thing, interesting thing in trying to build a quantum computer, that there are two possibilities. Either we can entangle a large enough number of excellent qubits and then we have a quantum computer, or we have to face a kind of limit, okay, which tells you, hey, you cannot build a quantum system beyond that size. And my hope is that maybe we find an interesting limit, an interesting borderline between the classical world and the quantum world. And in both cases, I am winning, because if Pascal can build a good quantum computer, I'm winning. But if we find, or if they find, a fundamental law of physics showing where is the limit between the classical and the quantum world, I win as a physicist who wants to know the answer. So I think that it is a very important problem which is not so far in front of us.
Bill.
Well, as Alain was speaking about the possibility of fundamental limits, of course, this would be such a wonderful thing to discover, because it would represent a new direction in research that is totally unanticipated. I would be very happy to have a bet about whether such a limitation would arise, or for that matter, whether it turned out that quantum mechanics was not limited in the way that we normally think that it is by things like the uncertainty principle. My very firm feeling is that we've got it all right now. That is, quantum mechanics describes both the limitations and the lack of limitations that we have. On the other hand, I would love to see myself proved wrong, because it would be such an exciting new development in quantum mechanics. And I think having a bet sometimes can help to focus people's attention on the possibility of learning something new. In fact, I have a bet already with Carl Williams about whether we're going to have a quantum computer anytime soon that can do something as difficult as factoring large numbers. But that's another thing entirely. But I think maybe it is time to get to the questions of our audience.
Well, thank you very much, Alain. Thank you very much, Bill. Thank you very much to IUPAP and UNESCO for hosting this. It's been fun to hear you both. And please, Silvina, go ahead with the question.
Okay, so yeah, thank you. It was very, very interesting. So I'm going to read some of the questions. We have already 11. I don't think we will be able to answer all of them. Not all of them have a indicate who should answer. So, but anyway, I will ask some of you to answer. So the first question is from Marcelo Terracunha from Brazil. And he asked, did we succeed in making the random citizen more aware of what quantum brings that classical views are not able to during this international year? If not, which path shall we try in the near future? So I don't know if Bill wants to answer that.
Well, like Alain, I've been giving talks about quantum mechanics during this year. This year has been the existence of this year has been a wonderful motivation and platform for giving those kinds of talks. And in those talks, I have emphasized that quantum mechanics gives us a different view of the nature of reality than what existed in the 19th century and earlier. And I think that people who have attended these kinds of talks have, in fact, understood that there is something different, that quantum mechanics really brings something that's fundamentally different, not just scientifically, but in a certain sense, philosophically. And I think that that's been an appealing feature of such talks. In fact, I started this by giving a talk at the opening ceremonies in Paris at the UNESCO headquarters, and a few people who were part of the staff said, I think I'm finally understanding a little bit about what quantum mechanics is about.
Okay, thank you. So let me move to the next question that I'll ask to Alain. This is from Hamed Barakat, and it says, regarding understanding quantum mechanics, I have two questions. Even today, when we analyze a new system or interaction, we begin from the classical picture, then quantize. Does not that mean that classical physics will always be a priori? What is meant by understanding here? A clear visualization in an aided perceivable world. Some of this has been answered, but the first one not. So Alain, if you can respond.
Well, I think it's not that simple. Yes, when we have a problem, we describe some objects in our real world, but as soon as we use the formalism of quantum physics, for instance, we use an Hamiltonian and something like that, immediately, if there is more than one object, we have to go in an abstract Hilbert space. And then things happen in that abstract Hilbert space. And the difficulty is to trying to have a correspondence between what happens in that abstract Hilbert space and the initial classical picture that we have. And then I must admit that for me, I use crazy images. I said it already, totally inconsistent. But because I am used to it, I can juggle with that, okay? And of course, the judge at the end of the day, the judge is writing equations. But for me, before writing equations, I need to get an intuition, and my intuition is kind of inconsistent, and I would even say sometimes irrational in the usual classical way of classical logic. And okay, there is nothing more I can say, but at the end, you need to use the formalism to see if this intuition that you get from some kind of bizarre intuition, does it work? And but to answer a few words about the question, do we think that this talks to general public changed something? My point of view is the following. You have the people who are complotists, who think the earth is flat, etc. There is nothing we can do with this one. Then you have the people who love science and they enjoy very much listening to us. But I am really mostly interested in the one who are in the middle, who think that science is good, but they are not 100% sure. And so our job is to convince them that yes, science is good. It is these people in the middle that we must convince, and it is my target when I give general talks. I don't care for the complotist, okay?
Okay, thank you. So the next one is a little bit like a, I don't know, Dan Kurtikapian asks whether the theory of relativity or quantum theory have had the greatest impact on our standard of living. Which one do you think of these two
No, I don't think
theories?
so. Quantum mechanics have had a much stronger impact on our lives. Relativity had basically no impact on our lives. While quantum mechanics, as we said, inventing transistor, laser, computer, etc., you could not do that without quantum mechanics. But relativity, basically, we don't need it. As soon as you know that light and electromagnetic waves travel at the velocity, at a constant velocity that we know, what else do we need to know in relativity for our lives? Basically,
But there's
nothing.
an exception to that. And the exception is the gravitational redshift in general relativity. If we did not understand Einstein's gravitational redshift, the satellite navigation system wouldn't work. We have to take it into account.
I know that you are right, but on the other hand, let's suppose that we don't know general relativity. The engineers would have observed that there is an extra term to add, and they would have added empirically, and navigation system would still work as well with an empirical term. So you
Well,
are right in principle, but we don't need to understand general relativity to correct for the navigation.
that's
What
probably
is
true.
important for the navigation is atomic clocks. Yes, this is important.
Yes, and that's a quantum mechanical thing,
Exactly.
and I absolutely
Exactly.
agree with
Exactly. Yeah.
that it's quantum mechanics that has had the most impact on our lives. But this also
Absolutely.
leads to a comment on a previous question about how we start with a classical system and then quantize it, and that has worked beautifully for any number of things, but not so well for gravity.
Oh,
Not
yes.
yet.
Not yet, but it's a lot of really smart people have been
It's
working.
still a very open question.
That's right. And it might be an indication that that's not the right way to go about it.
So I'm sorry, I'm going to skip some questions. You've already answered the role that quantum played in technology. You mentioned many technologies that grew out of quantum mechanics and quantum science in general. But I'm sorry for all the questions I'm skipping. But let me go to this one. Regarding the training of this is Nadine Weber. Regarding the training of the future quantum workforce, what in your opinion is most important to teach students or the general public about quantum technologies in the sense of what skills will be needed to actually work with quantum technologies in the future? For example, mathematical formalism, misconceptions, quantum ethics, etc. So let's start with Bill and then we go to Alain. And I guess this will be the last question.
Well, I'm not sure that my view here is very mature, but I think that often there is the idea that there's something particular about preparing people for a career in quantum technology. Whereas my feeling is that the kind of preparation that allows you to jump into a, um, uh, a job in quantum technology is essentially the kind of training that any good physicist needs. uh, and Sure, there may be less about plasmas and general relativity and more about atomic physics and condensed matter physics. But I think it's the same kind of training that we've been giving people all along. But maybe Alain has a more mature
Yeah,
understanding.
yes, I love teaching, and I think that the answer depends at which level. If you have to have the most advanced level, then mathematics is requested. But for, as I told you, when I was at the last year of high school, our teacher showed us some wonderful things like, okay, and if you want to know what is the radiation emitted by an atom, you have levels of energy, it emits a single photon, and you must complete that by saying, but you know, on the other hand, you have just to describe things. You describe wave-particle duality. You know, it's a fact, okay? This photon which has been emitted by jumping from one level to the other one, you send it on an interferometer and you observe interference on it. And you just describe things. And I think that if you describe many things like that, it's more than enough for people to appreciating the fact that the images and the concepts are different from the ones you have in the classical world, and you don't necessarily need to have mathematics. Mathematics is for people who will have PhDs and this kind of thing, and if we want to develop quantum technologies, we need to have many more people than the ones who do PhDs in quantum physics. We need to have people who are good engineers and not necessarily mastering the whole subtleties of the mathematics. I think that if you describe, you know, when I give my general public talk, I present this wonderful experiment that we did with Philippe Grangier. You send a single photon, a beam splitter, you show that it goes either on one side or on the other side, and then with the same source, same beam splitter, you recombine and then you observe interference. In the first part, you have something going either on one side or the other one, and in the second side, that same thing goes simultaneously. If you show that it is a real experiment, etc., at the end, the people will have a quantum mind, I think.
Thank you, because there are other questions about how to train engineers, which I think is very interesting.
Describing experiments, describing real experiments.
So, and let me include a very last question from a high school student that is here. I don't know where he's from, but his name is in Spanish, Carlos Javier Villamil Alvear. And so he asked what skills should the next generation have to advance quantum mechanics, but also he's asking, where can someone like me start, a high school student? What would you recommend for a high school student interested in quantum mechanics? I don't know if, Bill, you want to say something?
One of the ways in which we have interacted with high school students is that often a student will contact us and say, would it be possible for me to work with you during the summer? And we make the right kind of arrangements, and we've had some amazing and wonderful high school students working with us during a summer, and then sometimes that will extend to a longer relationship, and who knows, sometimes they'll enter the university and continue the relationship either with our group or with another group. So one of the ways in which this can be done is contact the local university. Look on the web, see who's doing quantum science that looks interesting and exciting to you, and see whether they have a place for a high school student.
I don't know exactly what to answer to this high school student, because I'm deeply convinced that there are some good books of popularizing quantum physics, but I don't know them in English. But I am sure that there are good books. Now, what they should do is really go to university and check the first year programs and select their major as a function of the first year's program. I think you cannot avoid, if you are serious, you cannot avoid studying seriously in a university, and you have to take exam and things like that. You can read about quantum mechanics and it gives you an idea, but at the end of the day there is a moment when you must learn. And a recommendation I should do to students, and it seems to be contradictory with what I said previously, but not at all, I will explain why. High school student, please study mathematics. Mathematics is a universal language for physics. okay? And you need to have good notion of mathematics. This is not contradictory with the fact that you don't necessarily need the special mathematics for quantum physics, but the general math, you need to have it. Otherwise, you don't know the language of science.
Okay, so thanks a lot. We are going to close the question from the public. I'm sorry, apologize for those of you that I couldn't read the questions. Thanks, Louise, and I give the floor to Amal, who is going to say the closing words. Thank you.
Thank you very much, Silvina. Thank you so much, Alan. Thank you very much, Bill. I really, really enjoyed this discussion a lot. And I'm sure you recall we opened the International Year with the opening ceremony here at UNESCO with you both present and giving wonderful talks. And now we end the year somehow also with you both. And so really, really thank you so much. It was excellent discussion. And I'm sure the over 300 participants with us here also enjoyed this discussion a lot. So colleagues and distinguished guests, on behalf of UNESCO, I'm really truly pleased to offer a few reflections as we conclude the 2025 Physics for Society Colloquium Series, organized jointly with the International Union of Pure and Applied Physics under the umbrella of the International Year of Quantum Science and Technology. And here I would really like to thank Silvina and Christine and Jing and Lassie for their commitment and for their excellent coordination of this colloquium. As the United Nations lead agency for sciences, UNESCO has long championed the vital role of basic sciences in driving innovation, strengthening education, advancing evidence-based policy making, and shaping the future of sustainable development. In 2025, through the International Year of Quantum Science and Technology, we launched this flagship colloquium series not only to highlight scientific excellence, but also to spark public dialogue and promote science as a shared human endeavor. With more than 2,500 participants across the 5 sessions, the series has become a platform of genuine global exchange, inspiring new ideas and opening new pathways for collaboration. One notable highlight was the June 2025 lecture by Professor Andrew Forbes of South Africa, whose work on quantum structure light resonated strongly with ongoing efforts to strengthen the quantum ecosystem across Africa. This event helped lay the ground for a broader discussion on regional quantum roadmaps and research leadership. Just last Friday here at UNESCO, we hosted a big event on science diplomacy and capacity building through synchrotron science in Africa, and this had participants from SESIMI, from ESRF, and from other leading facilities. Inspired in part by this colloquium series, this event explored how large-scale research infrastructures can contribute to regional scientific development and also to foster long-term cooperation. As we look ahead, I am proud to share that UNESCO will soon launch the global report on the International Year of Quantum, which synthesized the insights and contributions from across the year. This report is not just a record of events, it will be a forward-looking document that outlines global priorities in 5 key areas: policy inclusion, open science, international cooperation, capacity building, and inclusive innovation. These 5 pillars also underpin how the next phase of work. The launch of the UNESCO Global Quantum Initiative. This is a multilateral effort to co-develop an inclusive and responsible global quantum agenda for 2026-2030. This initiative, along with the global report, will be formally presented at the closing ceremony of the International Year of Quantum Science and Technology that will be held in February 2026 in Accra, Ghana. We warmly invite all of you to contribute and to be part of this new chapter. Let me close by thanking all the speakers, the partners, the participants who made this series a success. physics and science more broadly is not only about discovery, it's actually about the connection, inspiration, and the collective pursuit of progress. And I would like to end by paying special thanks to my colleague Jing Zhao, who actually is putting a lot of effort in the international year, in the implementation of the year, and also the coming reports. Thank you for being part of this journey, all of you, and we look forward to continuing this conversation with you all. Thank you very much. Silvina, over to you.
Thank you. No, I have nothing else to say. Thank you all. Thank you, Louise, Bill, and Alain. It was wonderful. Thanks.
Thank you. Thank you very much.
See you next year. Bye-bye.
Bye-bye. Thank you. Bye.
Thank you.